In this video, we're going to obtain an expression for the energy stored in a spring. Now what we know is that the spring force is a conservative force. So this Fs that we know, we understand that it is a conservative force. And if you recall from the definition of conservative forces, what you know is that the work done by this force is simply dependent on the initial and the final point. It does not depend on how you get to it. Okay, so once we know this, what we'll do is we'll find the work done by the spring force first, and then use the definition of the change in potential energy to figure out the potential energy stored in the spring. Now, what we know is that the spring force, the spring that obeys Hooke's law, satisfies this equation for the force. Now, clearly here, the force is changing. Now, Fs is varying rather. Fs is changing, and it changes depending on the change in x. So clearly this force is not constant. So Fs is not constant. Now this poses a slightly difficult situation for us. What we know is that what we've defined W as Fd cosine theta. That definition can only be used when the force is constant. So W equals Fd cosine theta only works when F is constant. This is important. Okay, so this works only when F is constant, which means that if F is changing, we need to alter this definition. Now you can do this in calculus by taking infinitesimal extensions of the spring and then finding the work done for each of the extension and then adding up all the work. So that's a straightforward procedure in calculus, but of course we do not have calculus at our disposal right now. So we're going to use something slightly different, something that we've already used in the past when we studied one-dimensional motion, where we had to find distances given the velocity versus time graph. So we'll do something similar. What we'll do is we'll draw a graph of the spring force versus the spring extension. And you see that since Fs is negative kx, negative k times x, this would be a graph with negative slope that passes through the origin. So now, to find the work done by the spring, let's say if we were to take the spring and if we were to extend the spring from, say, it's 0, the spring extension would go from 0 to, say, some value x. Okay, our goal is to figure out what the work done is. Now if you look at the work done is a product of the force times the x, force times the displacement. And if you recall from our 1D motion, what we said was, since distance was a product of velocity times time, the way to obtain that from a graph would be to simply find the area under the curve. So what we'll do is here, in order to find the work done, we will simply find the area between the curve and the x-axis, the shaded area here. And you notice that clearly that area is below the x-axis, and as a result of which the work done by a spring is always going to be negative. It is going to be minus 1/2 times k times x squared, which means that when you compress a spring, it does negative work. When you stretch a spring out, it ends up doing negative work, because the direction of the spring force is always opposite the direction of the extension. So the negative sign here implies that the Fs is opposite x. And this is what we know. When we studied friction, it was the same thing. Friction, the work done by friction when an object is sliding through a surface, was negative because of the angle being around 180 degrees. So here we get the same thing. So once again, the way we obtained it is by not using W equals Fd cosine theta, but by finding the area under the graph. And since we know that Fs is minus kx, we end up having a graph with negative slope, and then we find the work done by simply finding the area, and it's a triangle. The area is simply half of base times height. The base happens to be x, and the height happens to be k times x. So it is simply negative 1/2 times k times x squared. So now this gives us a very simple way of figuring out the change in the potential energy. This is equal to negative of the work done by the conservative force, and in this case, since we are interested in the spring force, this is what we get. So it is minus 1/2 times, minus of minus 1/2 times kx squared. So the change in the potential energy, the PEF minus the PER, is equal to 1/2 kx squared. Now, we can make life a little bit easier for ourselves by saying that, hey, when the spring is unstretched, when x is equal to 0, which means the spring is unstretched, we can say that the potential energy in the spring is 0, which means there is no stored energy in the spring when it is initially unstretched. So this allows us to simply obtain the potential energy of the spring as 1/2 times k times x squared. Notice that I didn't put the f there because I don't want to do the spring, but it's only f. But I'm saying that if the spring is compressed by a certain amount x, then the potential energy that is stored in it is going to be simply equal to 1/2 kx squared. And when the spring is unstretched, x is equal to 0, and so it has no potential energy. This is a very useful expression, and we will use this in the next video in trying to figure out the speed of an object, and we'll do a lot of other difficult things with this. Alright, so the potential energy stored in the spring is 1/2 kx squared. The work done by a spring is negative 1/2 kx squared, and the negative sign simply tells you that the spring force is always opposing x. So since if f and x are in the opposite direction, the work is going to be negative. So make sure you remember these two things, and also the process by which we obtained it. And what we did is we found the work done by determining this area under the curve, as we could not use FD cosine theta, because FD cosine theta works only when f is a constant. So keep this in mind. FD cosine theta works only when f is constant. When f is variable, we can either, later on in life you will end up using calculus to figure that out. But in our case, what we'll do is we'll find the work done by simply finding the area under the force versus the position graph. Alright, so the potential energy due to a spring is 1/2 kx squared. We're ready now to apply this to problems. Alright.